Okay, so now we're going to consider a method which is related to shake, known as the rattle method. And if you recall, the reason why one wishes to consider an alternative to shake is that the shake method results in positions which stay on the constrained manifold, but the velocities may not be in the tangent space to that constrained manifold. Okay, so and as we sort of alluded to, it's like the way you try to fix this is by introducing additional Lagrange multipliers, which then can be tweaked. It's like to guarantee that the velocity satisfies the condition for being in the tangent space to the constrained manifold. Okay, so so you want to construct a method that is a mapping of the tangent space to the constraint manifold to itself. All right, so that's, if you will, the motivation for this rattle method. Okay, and so again, the idea is that you correct the shake solution so that it lies on this tangent space through an appropriate projection. Right, so the idea is to correct the shake solution such that it lies on Tm, right, through an appropriate projection. Of the velocity Vn plus 1 onto the tangency constraint. Okay, and then the method you end up getting is what's called the Rattle Discretization. Okay, so again you have Qn plus 1 is equal to Qn plus h times V at n plus half. All right, so that's much just the same. And then mvn plus half is equal to mvn minus h over 2. So now I've sort of expanded this thing back out, if you recall. So this in the original Sturmer-Levy method, it's like was broken up into two parts, right? So the 2 half steps. So I'm sort of reintroducing the 2 half steps now. Okay, and then I'm going to have 2 different sets of multipliers. One for the, if you will, for the positions. It's like, and one for the velocities. Okay, so I'm going to denote the position ones by R. Yeah, well, maybe I should think of write that as Q, just to be consistent in notation. Okay, and then you have conditioned that G at Qn plus 1 is 0, so that's one condition you want. And then mv n plus 1 is equal to mv n plus half minus h over 2, the gradient. All right, so I've broken it up into 2 steps because, if you will, right, so this together with this allows me to update the position at the new time. It's like, and there is freedom here through this lambda sub q term. It's like, and the constraint, it's like to guarantee that this q n plus 1 stays on the constraint configuration manifold M. Right, and then now it's like the second piece now is aimed to guarantee that V at n plus 1 is on the tangent space, it's like 2m. Okay, and so here I have a multiplier term, but now to constrain the velocities, if you will. Okay. All right. Lambda v n. Okay, so this is to give me the flexibility to then satisfy the tangency condition, right? And if you recall, the tangency condition is that the gradient of the constraint functions, it's like dotted with the vector vanishes. Okay, so if you recall, big G is the is essentially the Jacobian, it's like of that vector value little g. Okay, so that's playing the role, it's like of each of the individual gradients. Okay, and then this has to be paired with Vn plus 1, and it has to vanish, and this is again a zero vector. All right, so both of these are zero vectors. Okay, so so that is what is called rattle. Okay, and then the lambda qn multiplier sort of enforces the position constraint. And the lambda vn multipliers, or multipliers, sort of enforce the velocity constraint. Okay. So let's see what you can do with this. So in particular, how do you solve for these velocity multipliers? Okay. So as you might expect, it's like as before, it's like you can solve for these multipliers by solving some linear system, right? So you solve for lambda v, right, and by the linear system, right? So g at qn m inverse g at qn transpose times lambda vn is equal to g qn 2 over h vn minus half minus m inverse the gradient of the potential qn. Okay. So in essence, it's like what you're doing here is that you're using this condition, right? And you're writing Vn plus half well, okay, what you're really doing is that you're writing Vn plus half, it's like as m inverse of the right-hand side, substituting into this condition. And then it's like getting a linear equation which involves lambda sub v, and then you have to solve for that, and that's what you get here. Okay. So if you combine it with this equation, so combining sort of this equation with sort of the time-shifted version of this equation. Okay. Okay, so I'm going to time shift this back by 1, so that's m vn is equal to m Vn minus half minus h over 2, the gradient of v at Vn minus 1, sorry, there's a n plus 1 here. Okay, so that's just v at Qn minus h over 2 g at Qn transpose lambda v. And this is at n plus 1, sorry, at n. Okay, all right, so slight typos, if you will. Okay, so if you combine this equation with this equation, you get mvn plus half is equal to mvn minus half minus h, the gradient of v at Qn, right, minus h over 2 g Qn transpose lambda Qn plus lambda Vn. Okay, so so there are two multipliers then, and it's analogous to this one, but they're now two different multipliers. Right. So that gets you to a form which is quite close to shake, but it's not exactly shake. Right. Okay. So of course you determine this by solving this condition here. All right. So okay. So you get lambda Vn by solving sort of this one, right? And then lambda nq is chosen such that, right, g at Qn plus 1, right, equals to 0, but g at Qn plus 1 is g at Qn plus hvn plus half. Okay. So anyway, all right. So the point basically is that this Rattle method is formally equivalent to the shake method, except that the multipliers have been replaced, right? So Rattle is sort of equivalent to shake, so except that this multiplier lambda n, right, is replaced with one half lambda q n and lambda Vn, right? So so the difference, if you will, is what happens to the velocities at the integer time steps. But if you view them as sort of this mixed position at integer, velocity at half integer things, then the methods are equivalent, right? So these two are formally equivalent. As maps from Qn Vn minus half to Qn plus 1 Vn plus half. All right. So the difference again is what happens to the velocities at the integer steps, but at these half integer steps you're fine. Okay. So by suitably sort of initializing, both methods yield the same solution sequence, except for the velocity approximation at the integer steps. Okay. All right. Okay. So those two, it's like are again formally equivalent if you initialize things correctly, and yeah, again, the main difference, if you will, is what happens to the velocity. It's like at the integer steps, and in Rattle, it's like you're guaranteed through the use of these additional Lagrange multipliers that velocity variable is going to satisfy the conditions for being a tangent space to the constrained manifold sort of M. All right, so that's let me stop here.